So now we have discussed the equivalent circuit and the phasor diagram. Now we will see how to measure the synchronous machine parameters. Okay, of the synchronous generator model, the circuit model that we discussed, right? So what was the circuit? We saw that there was the generated voltage, we have resistance RA and the synchronous reactance XS. This is the terminal voltage. So what are the two parameters here? The resistance and the synchronous reactance. In order to find these, we make use of two characteristics. Okay, so first one is the OCC characteristic. What is OCC is? Open circuit characteristic. And the other one is SCC, short circuit characteristic. From these two characteristics, we will be able to find the parameters. First, we will see how to get the open circuit characteristic, or what we abbreviate as OCC. Okay. So, if the motor, let us say this is the synchronous generator. Now, the rotor is rotated at rated speed, right, by means of the prime mover. Now, we have the three terminals where we get the generated voltage. Now, we will not connect any load to it, we will just keep it open circuited. So, what will the per phase equivalent circuit look like? This will be EG, the resistance and the reactance XS. Okay. So, now the terminal voltage will be equal to the generated voltage because this is open circuit. So, you can write this is equal to EG since it is open circuit condition. So, now what did we do? We did not connect any load connected to the terminals. And what was the speed with which we rotated? At the rated speed. Prime mover is rotated at rated speed. Okay. So, now what we do? We vary the field current starting from 0. Okay. So, vary the field current starting from 0. Okay. So, that means first you will keep IF is equal to 0. Then what will be the terminal voltage, right? Now, record terminal voltage for each value of the field current. Okay. So, for IF is equal to 0, what will be the terminal voltage? The same will be the EG as well. Okay. EG will be equal to VT. Similarly, for the next value of IF, say 0.5 ampere, then what will be the terminal voltage? This will be equal to EG. So, what will be this value? So, like that we take the values of IF and EG. So, we will get various values. From these various values, we will plot the graph. So, this graph, what it is going to look like? If this is the field current and this is the internal generated voltage, and you are going to get a characteristic. Initially it will be linear and then it will start getting non-linear. Okay. So, this will start happening when the core starts becoming saturated. That means even after increasing the field current, the generated voltage is not going to increase in the same proportion. Okay. So, this is the open circuit characteristic. Now, if the core was not getting saturated, then what will happen? It will follow a straight line like this. Okay. So, this straight line is called as the air gap line. Air gap line will give you the characteristic if the core is not getting saturated. So, this is how you get the open circuit characteristic. Now how to get the short circuit characteristic? So this will also be similar only, right? Only thing is that we will short circuit the terminals in this case. In open circuit test, we have kept it open circuit. So we have the synchronous generator here. Its rotor is rotated using a prime mover. Okay. What will happen to the terminals? These are all short circuited. But we will be connecting ammeters to measure the currents. Okay. So what will be the per phase equivalent circuit? Per phase equivalent circuit you are going to get like this. Here it is going to be short circuited. This is EG, RA, XS, VT is equal to 0. Here VT is not equal to EG. So what are the steps involved here? We are going to short circuit the generator terminals. Next we are going to rotate the rotor at rated speed. Next we are going to vary the field current starting from 0. Vary the field current starting from 0. Okay. And just like in the previous case, previously we have recorded the voltage, the terminal voltage. Here we will record the short circuit current. The reason we are using 3 ammeters here is ideally the current that will be flowing through each of the ammeters is same, right? Balanced 3-phase system. But there will be slight variations, so we will get the average current. Okay. So record the current in each line, and you can take average value if they are not equal. Okay. But one important thing here is we don't actually need many values here compared to the open circuit characteristics. So why is that? Because the short circuit characteristic will be a straight line. So we will see why that is the case as well. First we will draw the characteristic. So this is the field current and this is the armature current. Then this is going to be simply a straight line. This is the short circuit characteristic. So what is the reason for it? We have two fluxes, right? Magnetic fluxes. One is the main field flux. This is produced due to the field current IF. Now what else we have? We have the armature magnetic flux. Armature flux. So this is produced by the armature current. Okay. And VAR will be in phase with the armature current. We are talking about the time phase here, right? So VAR will be in phase with current IA. So now what will happen? If the field current, field flux, main field flux, if you are taking like this, okay, then what will be the phase of the generated voltage? This is going to be 90 degrees lagging the flux, okay. Now what about the current, armature current? So if you see this circuit here, you have a resistance as well as a inductance. But in reality, this RA is going to be of negligible value. So the armature current that is going to flow here, it is going to be almost 90 degrees lagging with respect to the generated, internal generated voltage. So here you can draw the current phasor. If this is at 90 degrees with respect to the voltage, then almost close to 90 degrees you have the armature current. Okay. Now what about this armature flux? This is in phase with the current. So here you are going to get BAR as well. So now you can see that armature flux and the field flux, main field flux, they are almost in opposition with each other. So the armature flux that is going to be present in this condition, in the short circuit condition, is going to be demagnetizing, mostly demagnetizing in nature, right? Demagnetizing in the sense because it is completely in the opposite direction, it will try to weaken the main field flux. So the flux that is present, the overall flux that is present, it will be very less. And when the flux is less, then there is no question of saturation. Don't worry, we will write down these points one by one. Okay. One thing we have understood, that this armature flux and the main field flux, they are coming almost in opposition with each other. Okay. BF and BAR are almost 180 degrees out of phase. So that means the armature flux BAR is demagnetizing in nature. See, if BF is like this and BAR is like this, then there will be a cross magnetizing component as well as demagnetizing component. But here the demagnetizing component is very high. So that is why it is predominantly demagnetizing. Okay. So armature flux BAR is demagnetizing in nature. Therefore, the net flux, the net magnetic flux will be very less. Okay. And in this case, when flux is less, then no saturation of the core occurs. Okay, no saturation can occur. So when there is no saturation, then you can expect a linear relationship. That is why the characteristic, short circuit characteristic, is linear. Okay. So if you get a single value, it is more than enough. One single value of IF, for that value of field current, what will be the armature current? With that 1 point, you can find out the SCC. Okay, because zeros, it will pass through the 0, 0. So you will just draw a line passing through the 2 points and you will get the short circuit characteristic. So now we have the OCC, that is the open circuit characteristics, as well as the short circuit characteristics. From here, how do we get the synchronous parameters at a given field current or a particular field current? Okay. So the very first step is, from the OCC, what is OCC? It is the generated voltage as a function of the field current. So the very first step is to get the internal generated voltage, that is EG, internal generated voltage from OCC, open circuit characteristics, at that particular field current. Okay. Next step is, from the short circuit characteristics, we get the current. Get short circuit current from short circuit characteristics. So from here, if you observe the equivalent circuit, what will it be at short circuit condition? This is the armature resistance. You have the synchronous reactance. Since it is short circuit, you are going to have like this, right? The terminal voltage will be 0. Now what will be the current? The current is what you are going to get from the short circuit characteristic, and the generated voltage you are going to get from OCC. Okay. So why at OCC or SCC this generated voltage will be the same? Because it will only depend on the field current and the speed. Okay. So that is why you are going to get the generated voltage from the open circuit characteristic and the short circuit current from the short circuit characteristic. Once you get both of them, then from the equivalent diagram, what are you going to get? The synchronous impedance ZS, which is equal to root over RA square plus XS square. This is going to be equal to EG by I. The voltage by current will give you the impedance, the magnitude of the impedance. Furthermore, if you neglect the armature resistance, this is very small in comparison to the reactance, okay. RA is much less than XS. So in this case, you are going to get the synchronous reactance is equal to the generated voltage divided by the current, short circuit current. You can write as ISC. More accurately, you can write this as approximately equal to, okay. But what if you want to find the resistance as well? Then what you do? You do the DC test, right? You do the DC test to get armature resistance, and once you get the armature resistance, impedance anyways you can find from this ratio, so you can get the synchronous reactance. Okay, so this is how both the parameters can be found out using the OCC and SCC as well as the DC test. Now one word of caution here is, this generated voltage EG that we are getting from the OCC, it will not exactly be the same as the generated voltage in the short circuit characteristic. Why is that? In the short circuit characteristic, the machine is unsaturated, whereas in OCC it is saturated, right? So that is why there will be a slight difference, but whatever value of synchronous reactance you are going to get, that is more or less, it is not going to be very different, okay. So this approach is acceptable. So you can write down EG from OCC is the value you get when it is saturated. The core is saturated, whereas the EG from actual short circuit condition, this is going to be in unsaturated condition. Therefore, there will be a slight difference in the measured and actual synchronous reactance. Now one important parameter that you need to know is the short circuit ratio. Okay, so what is this and why is this important? So first we will see what is this short circuit ratio. So if you consider the open circuit and short circuit ratio on the same graph, okay, so that means this is the field current axis and the voltage we can take here as well as the armature current, okay. So OCC, how you're going to have something like this. So this you can write as open circuit characteristic, and the short circuit characteristic is going to be somewhat like this, right. Now say the rated voltage is somewhere here. This is VT rated. Then what is the field current at this point? Let this be IF dash. Now what will be this value? This will be the short circuit current, ISC. That means for the same voltage, that is the same field current, at short circuit condition, the current is going to be, we are going to take it as ISC. Now the rated armature current, let us say it is somewhere here. So this we will write as IA rated. Now this field current, this we will take it as IF double dash. Now this short circuit ratio is nothing but the ratio of IF dash and IF double dash. Okay, so you can write SCR is equal to, this is abbreviated as SCR. So this is equal to IF dash divided by IF double dash. What is IF dash? This is the field current to get the rated voltage. What is IF double dash? It is the field current required to get the rated current. Now if you take this angle to be theta, then what is tan theta? You can either write ISC by IF dash or also as IA rated divided by IF double dash. So that means what? You will have ISC divided by IF dash is equal to IA rated divided by IF double dash. So from here what you're going to get, IF dash by IF double dash, which is nothing but the short circuit ratio, is going to be equal to the short circuit current divided by the rated current. Now if you divide the numerator and the denominator with the rated voltage divided by VT rated, then what are you going to have? This is going to be the, what is this value? 1 by synchronous reactance, right? We know that the synchronous reactance that we have found out, this is equal to the voltage divided by the short circuit current at the same field current, right? Now this same field current is IF dash here. At IF dash we have the rated voltage. Okay, so that means you can write this part, whatever you have, this you can write as 1 by XC. What about this? This is the rated values. When you take, what will it happen? It will be the base values. Rated values are usually taken as the base values whenever you are finding out the per unit values, right? So IA rated divided by VT rated will give you the 1 by synchronous reactance, base synchronous reactance. Therefore you are going to have, therefore the short circuit ratio is equal to 1 by XS divided by 1 by the base value. So you are going to get 1 by XS divided by X base. Okay. So the actual value divided by the base value. What will it give you? It will give you the per unit value. Okay. So that is how you are going to get the short circuit ratio is equal to the reciprocal of the per unit value of the synchronous reactance. So this is the significance of short circuit ratio. When you know the short circuit ratio, the inverse of it will give you the synchronous reactance in per unit.